All right, so the purpose of this video is to walk you through the parts of the FRQ problems that I asked you to do for homework last time, which relate to accumulator functions in context, and to go over parts of the problems that I did not assign and the final problem that I also did not assign. So you should have already read these problems. The first is all about the fish entering a lake, and you've got these two rates of change, E of t, which is the rate of entering in fish per hour, and L of t, which is the rate exiting in fish per hour. I've already entered those into my calculator, and so I'm ready to go. So part A says how many fish enter the lake over the 5-hour period. So we've got a rate of change for entering, that's E of t, and to get to the number of fish, I'm going to take the definite integral of E of t from 0 to 5. And I'm going to let my calculator do that work. And I get 153.45, but it says to round to the nearest whole fish, the nearest whole number, so that would be 153 fish. And that's part A. So part B says, what's the average number of fish that leave the lake over the 5-hour period from midnight to 5 a.m.? So leave the lake per hour, so it's number of fish per hour. So we're still looking for an average, but we're looking for an average rate. So since I'm given the rate of fish that leave, and I'm looking for the average of that rate, it's going to be the average value of a function, which is 1 over b minus a, that would be the width of the interval, times the definite integral from a to b of that function. So again, I'll let my calculator do the work, and I get 6.059. Now, they didn't tell us to round to the nearest fish, so we're going to go ahead and say fish per hour. It makes sense because when you're talking about a rate, it could have been like 6,059 fish over 1,000 hours for that matter. This is just a unitized unit. So part C, at what time is there the greatest number of fish in the lake? So if you think about when the number of fish is greatest, that's when you would start by finding any critical points. Now, critical points are places where the rate of change equals 0. So the rate of change in this problem, the E of t is the number of fish entering, and the L of t is the number of fish leaving. So the rate of change of fish is E of t minus L of t. That's the total rate of change. And this would be the thing that I would want to set equal to 0 to find my critical points. Well, I've graphed this thing in the interval from 0 to 5. So I would be looking for the place where these two graphs cross, because that would be where E of t equals L of t, and that would make the subtraction equal 0. So when I look at this graph from 0 to 8, the graphs look like this. Here's E of t, kind of goes up and then down like that. And then here's L of t, comes in like this, looks like an exponential, and they cross about right here. Now that time at which they cross is 6.2035, so let's say 6.204. Now, up to that point, E of t is bigger than L of t, so there's more fish entering the lake per hour than are leaving. But after that point, L of t is bigger, which means there's more fish leaving the lake, so the population will be shrinking. So notice this is the only place where they cross. So up until that point, the population is growing, and then when they cross, L of t is bigger, so the population is shrinking, so this is the absolute max. Now you could go back to the candidates test to justify this, or you could actually just give the verbal explanation I just gave as an explanation for why that's the absolute max of fish. Now notice it didn't ask for the actual max, it just asked what time would it happen. So now, let's look at part D. Part D says, is the rate of change in the number of fish in the lake increasing or decreasing? So be careful how you read this. It says, is the rate of change increasing or decreasing? Not the number of fish, but the rate of change itself. So remember, this is the rate of change itself. If I plugged in a number here, that would tell me whether this rate of change is positive or negative. But that tells me if the actual population's increasing or decreasing. If I want to know if this rate of change is increasing or decreasing, I need to find its derivative. So the derivative of that would be E prime of t minus L prime of t. And so they're asking at 5, is this positive or negative? Does this make the thing increase or decrease? So if I find e prime of 5 and L prime of 5 and subtract them, that will tell me the answer to this question. So again, I reach for my calculator. E prime of 5 is like negative 6.802, and then L prime of 5 is 3.921. That's clearly going to be a negative number, so it is decreasing. All right, so that's the fish problem. Let's move on to the next problem. Now, when you read this problem, be careful. You're given a rate again, and this is a rate for people entering a line. And it's given by this piecewise function, but notice this piecewise function basically just says there are people getting on the line from time 0 to 300, and then afterwards there's no one getting on. And then you're given another rate, but it's almost like hidden in the problem, of people exiting the line. And that exit line rate is right here. It's a constant rate of 0.7 person per second. And then you're also given an initial value of people in the line, which would be 20 people in the line. So we're going to end up using all those pieces of information at some point during the problem. So let's talk about part A. How many people enter the line for the escalator during this time interval? So when I look at that, part A, that's entering the line, and we have the rate for entering is right here. And we know to get the number of people, we're going to do a definite integral, and we're going to go from 0 to 300 of that rate. And when I plug that into my calculator, I get exactly 270 people. Nice and round. So if you look at part B says during the time interval, there are always people in line. How many people are in line at time 300? Well, when you're trying to figure out the total number of people in line, and you've got like people going in and people leaving and people who were there to start with, you figure out the number by taking the starting number of people, adding the number of people added, which might be obvious, and take away the number of people who have left. Now, the starting number we're given in the problem. There are 20 people in the line to start. The number of people added will be the integral from 0 to 300 of the entering rate. But we've already done that. We did that in part A. That was 270. And then minus the number of people left, there's that rate that we were given of people leaving, constant rate of 0.7 persons per second. So there's two ways of doing this. Because this is a rate, I could do a definite integral again. Definite integral from 0 to 300 of that 0.7 with respect to t. And I could do that, use my calculator for that. Or because this is a constant rate, I could treat it like I did before I even learned any calculus and say, okay, people are leaving the line at 0.7 of a person per second, and 300 seconds are passing. Now that only works if the rate is constant. So don't do that if the rate is not constant. So I believe what I get is 290 minus 210, so that's 80 people. That's part B. So for part C, it says, what's the first time that there are no people in line for the escalator? All right. So when I look at this, at time 300, which it says after 300, we had 80 people in line. So we're basically trying to figure out how long it's going to take for that 80 people to go down to 0. Well, remember, at time 300, we no longer have people entering the line. So that adding the plus number of people added that we did up here, no one's entering the line anymore, right? So all we have to worry about is this 0.7 rate of people leaving. So what we want is to know how long it's going to take if 0.7 of a person per second leaves for that to go to 0. Now that's just like straight up a linear problem to solve. I think if you move the 80 to the other side and divide by negative 0.7, you're going to get, I got like 114.285 or so. But keep in mind, that's the time after, 286 I guess, that's the time after 300. So I want to take that and add it to the 300. Wow. And that should give it, that says seconds at the end, by the way. And that should give us the time when there are no people in line for the escalator. Now, I never round it to a whole second unless I'm told to in the problem, so I would just go ahead and round it to the thousandths always if I have to. Now, part D. Part D says, at what time is the number of people in line a minimum? So, again, I'm going to write out an equation for the number of people in line overall. So, people in line. Now, the way I'm going to do this, I start up with 20. I'm adding the number of people who came into line. So starting at 0, ending at some time. We don't know what. Let's call that X, though. Let's don't call it T. Or I can call it B. Let's call it B. Entering the line minus the number of people exiting the line. By the way, that L of t, this should have a dt here, that L of t is 0.7, that E of t is that function above. Now, when I want to minimize or maximize this, I'm going to take the derivative of it. So let's call this people prime. The derivative of 20 becomes 0. The derivative of this thing, because of the fundamental theorem of calculus, is basically E of b. And the derivative of this thing, because the fundamental theorem of calculus, is L of b. So when I'm looking for my critical points, I basically am looking for a place, again, where my entering and leaving rates are the same. So again, I would graph this on the calculator. I've already got my entering rate in my calculator. I'm going to go ahead and put my 0.7 leaving rate in. And I'm going to get two numbers where these two rates intersect. The graphs look like this. Here's my entering rate, roughly. Here's my exiting rate. And the two places where this intersect, one of them is 33.132, or 1.133. And the other one is at 166.575. So basically, I'm looking at these, and on the first rate, my rate of people leaving is bigger than the rate of people coming in. So it's decreasing coming to that point. And then my rate of people coming in is bigger than the rate of people leaving, so it's increasing, and then decreasing. So I'm looking for a minimum. So really the only places a minimum could happen are here at 33.133 and here at 300, which is my endpoint at which I'm looking. So I'm going to take these two numbers, 33.133 and 300, and I'm going to plug them into the people in line equation that I came up with to see which one gives me the smaller number. Well, I've already done the 300 people. That was in part B. So at 300, there were 80 people in line. So when I do this calculation for the 33.133, I get 3.803, which is definitely less than 80. So the minimum occurs at time equals 33.133 seconds. Now notice, and it says to the nearest whole number, find the number of people in line at this time. So the nearest whole number there would be 4 people in line. And then the justification, you could say use the candidates test. So that's the second problem. All right, so problem number 3. Notice again you were given two rates of change, one in which bananas are being placed on a table, that's f of t. One in which customers are removing bananas from the table, that's f of t. And one in which employees are stocking the bananas, that's g of t. But notice that they apply to different time intervals. Customers are removing from time 0 to 12. Employees are restocking it only from 3 to 12. So keep that in mind when we're doing these problems. So for part A, how many pounds of bananas have been removed during the first 2 hours the store is open? So we've done problems like this plenty. We have a rate of change for bananas being removed. We're going from 0 to 2. So from 0 to 2 of f of t. And I would pop that into my calculator. and I would get 20.051. And since it's pounds, you could definitely have a part of a pound, so I would go ahead and round it to the thousandths. And that would be part A. So when you look at part B says find f prime of 7. So literally I want to take this function that was in pounds per hour, and I want to take the derivative at 7. So remember, no hero math. This function is already entered into your calculator. You should be able to use your calculator to find the derivative. So I'm going to go to my calculator, I'm going to do the dy/dx command, and I'm going to find the derivative at 7. And I get negative 8.1195. I hate rounding up to a 0, so I'll just write 1195. And then it asks, what are the correct units and what's the meaning in the context of the problem? So the units, since F was in units of pounds per hour, this is going to be in units of pounds per hour, or you could write pounds per hour squared. Now what that means then is that the rate at which bananas is being removed, I think I said bananas are being removed, is decreasing by 8.1195 pounds per hour, and you could write it as pounds per hour squared, at time 7 hours. You want to include both the meaning of the rate of change itself and the meaning of the independent variable we plugged in, the 7. Cool. So part C, is the number of pounds of bananas on the display table increasing or decreasing? Give a reason for your answer. So remember, the total rate of bananas is going to be the rate of stuff being removed and the rate of stuff being put on. Now the employees are putting bananas back on, right? So theirs is G of T. That's going to be the positive rate because they're increasing the number of bananas. F of T is the rate of customers pulling bananas off the table. So that's going to be the negative one. And basically what I'm looking for is what G of 5 minus F of 5 is. Remember, G of 5 and F of 5 are actually rates. We don't need to find their derivatives to know how the bananas are changing. They're already rates. And I want to know if this is positive or negative, and that'll tell me whether this is increasing or decreasing. So again, I'm going to use my calculator to do this for me. So G of 5 is 11.533 or so, and F of 5 is 13.796. That's going to be a negative number, so that means the number of bananas on the table is decreasing because the total rate of bananas is negative. So now when I look at part D, how many pounds of bananas are on the display table, remember the amount of something is how much did we have at the start plus how much stuff was added minus how much stuff was taken away. All right, so the number of things we had at the start, this is the first time we've actually used this number, is 50 pounds of bananas at the beginning. All right, so we're going to start with that 50 pounds. We're going to add the number of things that have, the number of bananas that have been added. And remember that that is G of T, so that's the employees stuff. So when they're adding bananas to the table, it's going to be the definite integral of their rate, which is G of T. Now on this one, remember the rate doesn't start until time 3, so we don't want to start this at time 0. We want to start it at time 3, and we want to run it to 8, because that's when we want to know the number of bananas. And then the number of bananas that are taken away. So that's the definite integral of the customer's rate of change, which is F of T. And again, we want to start that where this one starts, which would be at time 0. So these start at different times because they don't both apply throughout the entire time interval. But it will end at time 8 because that's when I want to know the number of bananas. So now I'm going to pull my calculator and do this calculation. And when I put that into my calculator, I get 23.347 pounds of bananas. I will do the last problem on a separate video.